Hello. In this video, we will be extending our knowledge about how to take derivatives with what are called the product rule and the quotient rule. So far, you can take derivatives of a lot of different functions, but there are some you don't know how to do, or it would be very tricky. These are not simple formulas, but they're very useful formulas. So let's just jump right in. The first one here is called the product rule. So suppose we have a function that is the product of two other functions. So here I'm just saying it's f of x times g of x. Here is the rule. If we have this, then the derivative of that function is given by h prime of x is f prime of x times g of x plus f of x times g prime of x. So let's just kind of think about the pattern here. We are adding two things together, and each pair is very similar. You'll notice on this side, it's the derivative of the first one times the regular original of the second one. And here it's the other combination, right? So it's kind of like these mixed doubles. One side has a function and a derivative. The other side has the different combination of a function and a derivative, and we're adding them together. So just a couple of comments before we start using this. I don't think anyone would say this rule is obvious. There is a reason why it's true, but it's certainly not obvious. And something you want to have in the back of your head, really all the time, is every time you're about to take a derivative, ask yourself, which rule are you about to use? If you can't verbalize the rule you're about to do, it suggests you're about to make up a rule. And the chances that a rule you simply make up is correct, very unlikely. So you really want to get in the habit of pausing, looking at your function and saying, how am I going to do this? Because if you just start randomly writing stuff, it's almost certainly wrong. So if you notice you're multiplying two functions together, you can say, all right, I'm going to use the product rule. And then pause, make sure you're applying the product rule correctly. Regardless of the functions involved, the product rule always follows the same pattern. So I would recommend using parentheses to create this pattern. So the idea here is the general form of this thing is when we're doing the product rule, it's something times something plus something times something. So what I do sometimes, and what I recommend you do, is once you know it's going to be a product rule problem, just write this pattern, right? Something times something plus something times something. Then one at a time, fill in these parentheses. It's especially good because the parentheses will already be there and you won't have to remember to add them. It's always this pattern. Just write the pattern first and insert what you need. I will just point out that in your textbook, the exact order in which they write this stuff is slightly different, but I promise you it's exactly the same formula, just presented in a different way. Don't get caught up in the names f of x and g of x. This is just a generic example where I'm multiplying a function named f by a function named g. We could have formulas, we could have other names. I really just like to think about it as I have the first function and the second function. So I really think of this as derivative of the first function times the second function plus first function times derivative of the second function. I'll write that here. Okay, so it's sort of like first prime times second plus first times second prime. That's not very good mathematical notation, but it's recognizing the pattern instead of getting caught up in, oh, which one is called f and which one is called g. If we are multiplying two functions together, we have to use the product rule. But if we have a number times a function, we don't. So let's just look at an example here. If I tell you that f of x is x cubed times sine of x, we would look at this and say, all right, x cubed is a function. Sine of x is a function. So I have to use product rule here. But if I say f of x is 5 times x to the fourth, well, that's not function times function. That's just a number times a function. We have a constant here. And our rule is if we're just multiplying by a constant, that just kind of hangs out. So our derivative, that 5 is just going to stay there. And then we multiply by the derivative of x to the fourth, which is 4x to the third, and then we could simplify. So not literally every case of multiplication uses the product rule. It's really when it's function times function. Functions, plural. And I'm not showing you where this formula comes from. You really don't need to know that in order to use the formula. But if you're curious, I can show you. Right? There's some trickery involved with algebra and limits. It's not super complicated, but I'm just choosing to leave it out here. Okay, so let's do a couple of examples. So suppose k of x is quantity x squared minus x times quantity 3x plus 1. So without foiling, find k prime of x. Right? So because we could do the algebra first, but I want you to practice using the product rule and simplify your answer. So you'll notice I always label things. If I'm about to take k prime, I write k prime of x equals. I don't just write stuff. Everything I write should have a label on it so it's very clear what it is. K prime of x equals, and I'm looking at this, it's a function times a function. I'm going to use the product rule. So before I worry about any of the details, I'm going to create that scaffolding for how product rule works. It's something times something plus something times something. And now I can start to fill things in. So the pattern is derivative of the first thing. Okay, that's 2x minus 1 times the second thing, 3x plus 1, plus the first thing, x squared minus x, times the derivative of the second thing, which is 3x. So that is a version of the derivative. And now I really should have said without foiling first. So what we could do now is simplify what we have. This is a version of the derivative. We might want to clean it up. So I will foil this part. So first is 6x squared, outers is 2x, inners is negative 3x, last is negative 1. And then over here, I just distribute the 3. So I would have 3x squared minus 3x. So I'll just group my like terms. 6x squared and 3x squared is 9x squared. In terms of my constants, I have 2x minus 3x minus 3x. So that is minus 4x, and then minus 1. I think I misspoke there, but it looks like I've grouped things together. So for this one, we could have foiled first. We could have foiled later. Maybe it's the same level of difficulty. You'll see other examples where it's very clear we want to do product rule. Another example, so suppose we have this function. M of x is root x plus 2 times negative 3x plus 1. The graph of this function passes through the point 4 comma negative 44. Okay, we're just given that. Find an equation for the tangent line at this point. So we want to pause and say, okay, we're trying to find the equation of a line. That is the instruction. So we want to understand, what do we need? To find the equation of a line, we need a slope and we need a point. We've already been told where the point is. So we need to find the slope of a tangent line. The slope of a tangent line is a derivative. So let's compute that derivative by doing product rule. So m prime of x equals product rule setup. And I'll fill these in one at a time. So square root of x is the same as x to the 1/2. So the derivative of that is 1/2 times x to the negative 1/2 plus the derivative of 2, which is 0. So I'm going to write the plus 0 just to make it clear that I thought about it. Derivative of the first thing times the second thing. So I'm just copying the second one. Plus the first thing, root x plus 2, times the derivative of the second thing, which is negative 3 plus 0. Derivative of x is just 1. So this derivative is negative 3. Derivative of constant is 0. Now, this is unsimplified. The hint that I'm giving you here is We don't really need a simplified version of this formula. What we want to know is what is the slope at a particular point. So we want to know the slope of the tangent at x equals 4. So that means we want to find m prime of 4. What I would recommend is just plug it in first, and it will be easier to simplify. So we will have 1/2 times 4 to the negative 1/2. We'll simplify that in a second. If we plug it in here, that's just negative 12 plus 1, which is negative 11. Here we'll have the square root of 4 plus 2, and here we'll have negative 3. All right, I'll do a little bit of work here. The negative 1/2 power means it's a square root in the denominator. Square root of 4 is 2. This one, the numbers maybe are a little bit unpleasant, but from here it's just arithmetic. I maybe should have come up with a better example when I wrote this, but we'll get through. So this is 1/2, this is 1/2. And we're multiplying by negative 11, so that's negative 11/4. This is 4 times negative 3, so that's negative 12. And we should probably create a common denominator here. So I'm getting this rather awkward slope of negative 59 over 4. But, if the slope is that weird number, the slope is that weird number. So what we've learned here is that our slope is negative 59 over 4. Right? It's just a coincidence that m for slope and m for this problem are the same. Maybe I'll just write slope colon. My point is at 4 comma negative 44. So I'm just going to use point slope form because I don't want to deal with that fraction. Y minus our specific y coordinate equals slope times, in parentheses, x minus our specific x coordinate. That's the equation for that tangent line. You could clean it up if you want to, but the instruction was to find an equation, which means any form is fine. So this is just an example where we're doing things we've done before, finding a derivative, finding a slope, using that slope to find the equation of a line. But we have more tools at our disposal. We're noticing if the function has multiplication in it, we know what to do. And the same thing is true with division. That's called the quotient rule. So suppose we have a function q of x that's a quotient of two functions. Right? So f of x over g of x. F of x divided by g of x. Then here is the formula for the derivative, right? This is not easy, but it is the correct formula. So it's the derivative of the top function times the bottom function minus the top function times the bottom function, all divided by the bottom function squared. Right? And you'll notice I talked through this by just using the names top and bottom rather than f and g. Right? The pattern would always have something on top and something on the bottom. It wouldn't necessarily have something called f and something called g. Right? Again, this is not obvious. Right? This is not an obvious formula at all. So, same advice as before. When you're doing a derivative, every time you're about to take a derivative, ask yourself, what rule am I about to use? And if you're about to use the quotient rule, right, make sure you're doing it correctly because it is not an easy rule. Again, there's a pattern here, and I would recommend, once you know you're doing quotient rule, create that pattern, right? The pattern is, it's a big old fraction, something times something minus something times something, all over something squared. Let me make that squaring a little bit better. That's what I would do first. I am just creating the pattern. Two things multiplied together minus two things multiplied together, all over something squared. Then I have my structure ready. My parentheses are ready, and I'm just inserting what I need. Again, your textbook presents this in a slightly different way, if I recall correctly, but it's equivalent. Don't get caught up in the names f and g, right? I mentioned that before. Think of them as top and bottom. I strongly recommend that you learn these in the order that I have given you. because then you will notice that the rule for the product rule is extremely similar to, oh, that was not helpful. But the product rule basically looks like this numerator with a plus instead of a minus. So what that means is, if you remember the product rule well, the quotient rule feels like a modification as opposed to a brand new thing. Right, so I'll put the correct formula back. But they are very similar formulas, which means hopefully it's easier to remember them kind of together. Quotient rule has a subtraction in the middle, and it has that whole divided by g squared. Again, quotient rule is used for dividing two functions. So if I have y equals 3x plus 1 over x plus 4, right, that's a function divided by a function. I want to use quotient rule. If I have y equals a number divided by a function, I also want to use quotient rule. But where we don't need quotient rule is if we have a function divided by a number. Because anytime we're dividing by a number, we could actually say, oh, that's really just 1/3 times what we have in the top. And instead of doing quotient rule, we can just say, oh, I have that 1/3 hanging out in front, and then it'll multiply the derivative that comes next, which would be 12x squared minus 1. So if your denominator is a number, try rewriting it instead of using the quotient rule. The quotient rule isn't wrong, but it's overly complicated. It will slow you down, and it will increase the chances that you make a mistake. And as before, I'm not showing you the proof. Let me know if you want to see it. So let's just practice a couple of things, and then we'll be done. So differentiate this function. So here's what I want you to do. Right? Pause, and you try this as much as you can. Try to follow that pattern. Right, so my hope is that you really did this. V prime of x equals, I always label what I'm doing, and I'm going to create that scaffolding. Right? Just what is the pattern for quotient rule? I'm going to make it nice and big so I have plenty of room to put things where I need them. Something times something minus something times something all over something squared. And the rule is, the first thing is the derivative of the top, which is 7, times the bottom. Then after the minus, it's the other combination. The original function of the top times the derivative of the bottom, all over the bottom function squared. And now here, because we might need to do something with this, we often need to simplify. Derivatives are just a step for doing other problems. And right now we're mostly focusing on how to take derivatives well. But if I wanted to use this to answer a question, I'd probably need to simplify it. So here's what we've got. If I distribute this stuff, that is 7x squared plus 7x. And then for this other stuff, I will FOIL. So first times first, my outers are 7x, my inners are negative 2x, my lasts are negative 1. We're going to leave the bottom factor like that. That's okay. And don't panic about all this algebra. You will need to do some algebra in certain cases, but often I will set it up so that it's not horrendous. But if you're noticing algebra mistakes as you go, don't just sweep them under the rug either. Right? If you really are having trouble with algebra, talk to me, and I can try to help you out, try to make you understand it better, give you some practice, etc. So if we group all this together, same denominator, I'm going to leave that as is. For our x squareds, I have 7x squared minus 14x squared. So that's negative 7x squared. For my x terms, I have minus 7x, and then these have become plus 2x. So that actually works out to minus 5x. And then for my constant, I have 7 plus 1, which is 8. So not a very pretty answer, but that's the answer, right? We don't get to decide if this is an easy derivative or a hard derivative. The derivative is what it is. This is the function that measures the tangent lines for v. And if it's complicated, so be it. Okay, one more example. Use the derivative to explain why the graph of y equals 4x over x plus 3 never has a horizontal tangent. So horizontal tangents are going to come up a lot. Right? A horizontal line has a slope of 0. And the derivative measures the slope of the tangent line. So a horizontal tangent line basically means the derivative is equal to 0. Derivative measures slope of the tangent line. If the tangent line is horizontal, then the slope of the tangent line is 0. So I am going to do quotient rule. I always start by labeling what I'm going to write down. Do that first. If I am about to figure out y prime, I write down y prime equals. Then I look at this and say, all right, I'm going to need quotient rule. So let's very carefully just think about how quotient rule works. I'll fill in all the details later. So once I start filling in those details, derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And what happens when I simplify this? If I distribute up top, I get 4x plus 12 minus 4x all over x plus 3 squared, which is 12 over x plus 3 squared. So that's our derivative form. If we want to find a horizontal tangent line, it means we're thinking about when is y prime equal to 0. So if y prime is equal to 0, that means 12 over x plus 3 squared is equal to 0. And if I multiply each side by x plus 3 squared, basically cross multiplying this gives me 12 equals 0, which is impossible. So what that means is this never happens. We have a derivative that's never equal to 0. So if the derivative is never equal to 0, there's never a horizontal tangent. If you graphed this, there would be portions where the tangent line is almost horizontal, but there's actually never a point where the tangent line is completely horizontal. All right, that is it. You really want to just practice using this a lot because there's only so much I can say about how the formula works.